the natural numbers. So think of counting from 1, 2, 3, and so on. Will this be a field? Let's test and see. If you add 2 natural numbers, you get another natural number. Yes. If you have 3 or more natural numbers and you add them, will the addition be associative? Yes. But do we have the identity 0? Yeah. No, because we can see here that 0 doesn't belong to this set. So no, this is not a field because at least one of the axioms fails. Okay, good. This is not a field. Now let's look at another number system, which is the set of integers. Now, if you consider the set of integers, which we denote by Z, you just think of positive and negative whole numbers. So -1, -2, -1, 0, 1, 2, and so on. Now, in addition, yes, you have your closure, you have your associativity, you have your additive inverse, you have your additive identities. It will be commutative and addition. Now, when we go to the non-zero elements under multiplication, you have your closure, you have your associativity, you have your multiplicative identity, but will we have multiplicative inverses? Now, I'm asking, is there some element Q in Z such that if you pick an element 2 here, 2 times Q equal to 1. So that element Q will be a fraction, right? That fraction will be 1/2, but we can see here that 1/2 doesn't belong to this set. So there are some elements in this set that do not have multiplicative inverses. So this cannot be a field. So the answer here is no. So it means that this set here is not a field. Okay, so we've seen 2 non-examples. Now let's look at an example. So from integers, let's move to the set of rational numbers. So the set of rational numbers, you are just looking at what? The set of all fractions, a over b, so that a and b are integers with b not being 0. You can check the axioms and see that, yes, this would be a field. Now, if you consider a set of real numbers, then they also satisfy the axioms for a field. Let's look at a bigger set, which is the complex numbers. So you look at all numbers of the form a plus ib, where your a and b are real numbers, and I is just an imaginary number with I squared equal to -1. Then this is also a field. This is quite special in the sense that in algebraic geometry, you find solutions or roots to polynomial equations. And if you have a polynomial with coefficients from R, there are some equations that will not have roots being real numbers. But when you extend to the complex numbers, then all polynomials with coefficients coming from C will have roots in it. And we call that algebraically closed. So this is quite special in terms of a field. So the set of complex numbers is an algebraically closed field, which plays a very important role, especially when you are looking at what eigenvalues and eigenvectors, which we will look at later on in this series. All these examples here are examples of infinite sets which are fields. So that means they are very large. But can we look at some finite sets which are fields? Let's consider the 12-hand clock. We live in a 24-hour world, but we use a 12-hand clock. So usually when it's 1400, we say it's 2 p.m. Or we tell time by what? AM and PM. So AM means from midnight to 12 noon, and PM is from 12 noon to midnight again. Right? Now, how do we say that 14 is the same as 2 p.m.? We look at the remainder when 14 is divided by 12. And that gave us that's what 1400 is equivalent to what? 2 p.m. And in math, we call that modulo arithmetic. So modulo arithmetic, look at the remainder when you divide the resulting number by the modulo you are considering. So here we are looking at addition modulo 2. So if you have your sets containing 0 and 1, when you add two things, you look at the remainder when you divide it by 2. So 1 plus 1 is 2, but when we divide 2 by the modulo, which is 2, you get a remainder of 0. 0 plus 1 is 1, and the remainder is 1. 1 times 1 is 1, and so on. And you can check that this will form the axioms satisfy the axioms of a field. So this first example of a finite field. In general, if you have a prime number P and you consider the set ZP, which is 0, 1 up to P minus 1, and you consider addition and multiplication modulo P, then this will be a finite field. The reason we are considering prime numbers is that if you consider non-prime numbers, then some things can go wrong.